Hey everybody, it's Ripley back again. We're going to do a quick little summary of curve sketching. It's not going to take very long, but I want to do a couple problems with you just so you see how this works out. Okay, first things first. Let's keep it simple. We're going to do, let's do f of x equals, let's go x to the fifth minus 5x. Okay? I'm going to do everything. All right? I'm going to walk through the whole 9 yards. All right, so this basically brings up all of the stuff that we did back in Algebra 1, Algebra 2, and now what we know about calculus. I guess pre-calculus as well. All right, so first things first, let's talk about the domain of this thing. All right, it's polynomial, so we know that the domain is all reals. That's easy enough. Let's talk about, what else can we talk about? Let's talk about X-intercepts. How about an X-intercept? How do I find an X-intercept? Well, I take x to the fifth minus 5x, and I set it equal to 0, right? And that would imply, what do I got? X times x to the fourth minus 5 is equal to 0, right? So what is that? What do we got here? Good Lord. This is going to be at x. I get x-intercepts at x equals 0, which is nice. And x equals plus minus the fourth root of 5. Ye gads. How about, let's do y-intercepts. How do I find y-intercepts? Well, I know that if x equals 0 is the x-intercept, then that's the origin. Therefore, that's got to be the y-intercept as well. But the other way is just to find f of 0, right? Because I know that x is 0 whenever I cross the y-axis. So I get f of 0 equals 0, and I'm done. How about asymptotic behavior? Let's do any vertical or horizontal asymptotic behavior? No, because it's a polynomial. Okay, so the dirt work is out of the way. Now let's graph this sucker. So the first thing that I'm going to do is I want to figure out when it's, let's go, well, there's no asymptotes, but I'm going to co-op 4 here for just a second. I want to know when it increases and decreases. Okay, so I'm going to take the first derivative, f prime of x. When in doubt, take the first derivative, right? 5x to the fourth minus 5, set it equal to 0. Might want to factor out a 5 here, right? I get x squared, or whoops, sorry, x to the fourth minus 1 equals 0. Now, this you want to be really careful with because you can miss solutions if you get glib with this. I got 5 times x squared minus 1 and then x squared plus 1, and that equals 0. So sometimes what students will do is they'll go, oh no, it's at 1, I got it. But then they forget that I actually get plus or minus 1 from x squared minus 1 because that can be factored into x plus 1, x minus 1. X squared plus 1, excuse me, cannot be factored. So I know that I'm going to have critical values at x equals plus or minus 1. Then I'm off to the races, Ripley doodle diagram. And I've got f prime, and this is going to be negative 1, and this is going to be positive 1. Excuse me. We'll plug in negative 2. Where do I plug it in? Well, that tells me f prime, so I'll plug in negative 2. Let's put it here. Well, let's put it here. If I plug in negative 2, this whole term, this is going to be positive, this is going to be positive, everything's positive. If I plug in 0, I get a negative. And if I plug in positive 2, because, oh, we should look at symmetry. Is this even, odd, or neither? Well, if I plug in f of negative x, let's see, I'll just sort of wedge that in here. F of negative x is equal to negative f of x. Oh, wow. So therefore this guy's odd. That could save me some time, right? Anyway, let's get back to this. So plug in positive 2, I'm going to end up with a positive. So I know that this function goes up, it levels off, it goes down, it levels off, it goes up again. But I can answer the question about increasing and decreasing right now. I know increases from negative infinity to negative 1, union 1 to infinity. Again, we've seen all of this technique. I know that it decreases from negative 1 to 1. This is going to look a lot like that problem that we had before. All right. Now, how about let's put a 5 in here. We should call this like 3.1 or something. Let's put a 5 in here. How about max and min? Well, if it goes from increasing to decreasing, I got a max, right? So I know that I have a max at, let's see, where at negative 1 comma, and I can do this one relatively easy in my head. I'm not going to be so lazy. It looks like, what's that going to be? F of negative 1 is going to give me a negative 1 plus 5 is 4, right? Negative 1 comma 4. And because it's odd, ooh, I can use that. I know that there's a min at 1 comma negative 4, right? Doesn't that have to be? Well, check it. If you don't believe me, 1 to the 5th is 1, minus 5 is negative 4. Awesome. I know that with odd, x and y change signs, right? Excuse me. Or yeah, it's symmetric about the origin. I don't want to be too crazy about that. All right, so that takes care of that. I've got increasing, decreasing. I've got max, min. I got all this fun information. Now what am I missing? How about, let's go 6. I want to know when it's concave up, concave down, and then I'm sure that you're going to be like, well, Ripley, what about the inflection points? Well, we'll see those here in just a sec. So if I'm going to deal with concavity, I'm going to take a second derivative of x, which should be pretty easy to do. That gives me 20, what do I got? 20x cubed, right? Minus 0, so this equals 0. That's easy enough. I've got a critical value at x equals 0. All right, let's fire this thing up. Ba-bam, ba-bam. Here's f double prime. Plug negative in, I get negative. Plug positive in, I get positive. Now remember, this is the first derivative of the first derivative. So I'm not going to do my little sketchy here unless I was sketching the first derivative as well, right? Because that just doesn't make any sense. Excuse me. Okay, so we're good there. And then last but not least, how about, that should be a circle. That should be, how about inflection point? Well, first and foremost, does concavity change? Yes, concavity changes. Where does it change? It changes at x equals 0. Does x equals 0 live on this continuous function over here? Yes, indeed it does. So I know I have an inflection point at 0, comma 0. Now, I can kind of cheat over here if I want and just make it pretty. And we can make this guy go, I know that it's cubic like this, and I also know that it's odd. So I can stick, I'm going to put 0, 0. Wow, that's really hard to see, isn't it? Let's go red. Put a little red right there. I know that that point right there is 0, 0. That's the origin. So now all I got to do is put a guy here and put a guy there, and then we stumble over and take a gander and see how close we got. Ooh, there's my old one. Remember that one? Let's clear that out. And what did I have? X to the 5th minus 5x, right? So x to the 5th, where's my up caret, to the 5th minus 5x. Again, this is just a quick and easy summary. I want you to see sort of how, if you were sitting in my class, I would want things summarized, okay? Let's go zoom, zoom, and we're going to go standard, which is, where are we, 6, bam, and here it comes. Oh, look, we're so good. We nailed it. Nothing to it. Excuse me. All right, so if you were in my class, you know what though? Well, I would be remiss to not write when it's concave up, which I know, I should have been 0. Wow, I was a little lazy over here. It's concave up from 0 to infinity. It's concave down from negative infinity to 0. Now, for those of you that are super anal, this is a wonderful way to organize your work. It's a great way to organize your work. All right, it's easy to grade, it's easy to look at, and way more importantly, it's easier for you to go back and look at later and figure out where you made mistakes or what you were doing and when you were doing it. Okay? All right, I'm going to do one more, and then we'll be done. I want to do, how about f of x, we'll do the whole thing, is equal to, let's go x over x squared minus 1. All right? So first things first, always start with the domain, right? So that's going to be 1. We'll start with the domain. Should be relatively obvious. Excuse me. It should be relatively obvious that the domain of this thing is all reals except when the denominator is 0. So that's going to be when x equals negative 1 and 1. So we'll just say, we're going to cheat a little bit. We're going to say x can't be plus or minus 1. Right? So another way to say that is negative infinity to negative 1, union negative 1 to 1, union 1 to infinity, but this is kind of a cheater's way to do that. 2, how about, would you want to do x-intercept? Let's do x-int and y-int. Well, y-intercept is easy, right? All I got to do is plug in 0. Oh, look, and I get 0 again. Hey, that's kind of helpful, isn't it? So I get 0, 0, and if the y-intercept is 0, 0, then I know for sure that an x-intercept is going to be 0, 0, but there might be another one. Well, how would I do that? I'd set the function equal to 0. Yeah, only 0 turns this fraction into 0. Sweet, that makes it easy. Let's see, what am I missing? How about symmetry? Let's do symmetry. My symmetry will be what? Well, my symmetry, if I do f of negative x, I get negative x over negative x squared minus 1, and this turns into negative x over x squared minus, hey, this thing is odd. Oh, wow, this is going to be a lot like the other one. Maybe I should have picked an even one, but it's just a variation on a theme. How about asymptotes? Let's go. Horizontal asymptotes and vertical asymptotes. This is all just the dirt work to make our lives easier. Well, let's do horizontal asymptote. What's the degree of the top? What's the degree of the bottom? Or what's the limit in infinity? You should be able to see that that easily turns into y equals 0. What's the vertical, or what are the vertical asymptotes? Well, let's get rid of that. I'm going to erase that. Let's get rid of that. I can easily write this as, go away. I can easily write this as x over x plus 1 times x minus 1. And it's easy to see that as I approach x, 1 or negative 1, I end up in trouble. I end up with a limit at infinity. So this is going to be at x equals negative 1 and x equals 1. Okay, now we can do some mathematics. But we already know. Now this time, I'm going to put it over here. I'm going to draw just a little shell over here. So I'm going to have a stick figure like I had before, but since I've got these asymptotes and I've got some sort of crazy stuff going on, I'm going to poach just to make my life a little bit easier. I'm going to tweak my scale a little bit, and I'm going to make this x equal 1. And I'm going to make that 1, 2, 3. I'm going to make this x equals negative 1. And then I remember that the x-axis is y equals 0, so I might want to label that just to have it there. Now, let's do our thing. I want to figure out when it increases and decreases. Well, how do I do that? I'll take a derivative. F prime of x is equal to low d high, which is x squared minus 1, minus high d low, which is x times 2x, all over low squared. Now I get x squared minus 1 squared, and I set that equal to 0. And then I do some algebra. Remember back in the day when you didn't know when to stop doing algebra? Well, guess what? We don't have to worry about that so much anymore, because we'll know when to stop doing algebra because the function will work, or excuse me, the critical values will get spat out, which is what we're looking for anyway. So I'm going to clean up the top just a little bit. This becomes a negative 2x squared. So I end up with negative 2x squared minus 1 over x squared minus 1 squared equals 0. Ooh, this is interesting. Let me just flip this over to the other side. This is negative times 2x squared minus 1, or excuse me, plus 1. Ooh, that's always positive. That's going to be helpful. And then I've got x squared minus 1 squared. Now notice the only critical values are the places where I've got CVs at x equals plus or minus 1, the places where, not where the derivative equals 0, but where it doesn't exist. That's very interesting. That's intriguing. So let's look at what happens. I know that x equals negative 1, and I don't know why I did that. That was dumb. Just taking up space that I don't want taken up. If I stick x equals negative 1, I did it again. Don't mind this guy. And x equals positive 1. Those are where my vertical asymptotes are. So now all I got to do is check some stuff. Let's see what happens. I'm going to throw in, let's go negative 4. If I plug in negative 4, then this guy is always going to be positive. This guy's squared, so it's always going to be positive. Whoa, whoa, whoa. Easy there, Sparkles. There's that negative. Oh, wow. So this thing is always going to decrease, isn't it? Because this term's always positive, this term's always positive, but there's that negative there. So you might already be saying, Ripley, I already know what this thing looks like, but let's go easy. If it doesn't have any, well, hold on. Let's answer this question first. I'm sorry, I'm getting ahead of myself. Increases, never. Decreases, well, whenever the first derivative is negative. So we're going to say, now I got to write it out, which is a bummer. Negative infinity to negative 1, union negative 1 to 1, union 1 to infinity, and I'm done. How about 6? Oh, I'm going to try and write it down here, but I may bust myself. Let's go 6. What? 6. How about max and mins? Well, if you think about it, this thing decreases. If I draw my stick figure, then I've got this vertical asymptote, then it decreases again, and then I've got another vertical asymptote, and then it decreases again. Now, I don't necessarily know how that looks until I'm going to put it over here, right? But you can tell that there is no place from the first derivative for which the first derivative equals 0, which implies what? There is no max or min, because there's never a place, it's not a closed interval, and there's no place at which the first derivative equals 0. Well, that's interesting. All right, how about let's go 7, and we'll go CCU and CCD. Let's see, I got this. I want this as clean as I possibly can get it. And CCD, right? All right, so I'm going to do my second derivative. Now, we got to go slow on this one because this could get a little bit ugly. This is going to be x squared. This is going to be, oh, I made it angry there, didn't I? This is going to be low d high. So I'm going to have what? X squared minus 1 squared. That's low. D high, now I'm going to do this in my head just because it's going to be easier. This is going to give me a derivative of 4x and then times that negative 1. So I'm going to have negative 4x minus high d low. But I've got this negative on top. I've chosen to put it on top. So this is going to be plus 2x squared plus 1 times d low. Now let's see if we can do this one in our head. This is going to be 2. This is a chain rule, right? This is blah squared. This is going to be 2 times this quantity times the derivative of the quantity. So this will be 2 to, oh goodness, times x squared minus 1 to the first, or I'll just leave it like that, right? And then times the derivative of the quantity, which is 2x. The whole thing is over x squared minus 1 to the fourth now. Now this one's ugly. We're going to have to do quite a bit of dirt work on this guy. Maybe I'll come way over here so I've got some room to work. All right, well, what should we do? Notice I've got a negative 4x in both places, so let's get that out of there. If I pull the negative 4x out, wait, that's not a negative 4x. That's a positive 4x in it. That time just looks like a negative. Respect thy negative, Ripley. So I'm going to pull a positive 4x out, and this is going to leave this guy with a negative term. So I'll have, oh goodness, this is going to be, if I pull the positive 4x out, I will have 2x squared plus 1 times x squared minus 1 minus, because this negative right here, minus x squared minus 1 squared. Okay? 4x, I should probably put another parenthesis there just to make sure that I get it. This whole thing is over x squared minus 1 to the fourth. Now you might notice, I'm going to change colors so we can see it. I can actually cancel one of the x squared minus 1's here, right, with this guy and one of these guys here. So I can turn this into a 3, turn this into a 1, and that cleans this thing up algebraically just a little bit. I'll get 4x. Now I'm going to leave that 4x by itself because it produces a critical value when I set it equal to 0. So it's kind of sacrosanct. All right, this is going to be 4x times 2x squared plus 1. This guy's now gone. Minus x squared minus 1. I'll put the parentheses back around it, right, because that squared turned into a 1. This whole thing is over x squared minus 1 cubed. I'm doing algebra to simplify my job a little bit. I haven't even set this thing equal to 0 yet, have I? All right, so what do I end up with? I end up with 4x times, let's see, 2x squared minus 1x squared is x squared. And then I end up with 1 minus a negative 1. That's just going to be plus 2, isn't it? I'll buy that. All over x squared minus 1 cubed. When I set this equal to 0, x squared plus 2 produces no real solutions. But I do get a critical value at x equals 0 here, and then plus or minus 1. So when I do my Ripley-Doodle diagram, this is f double prime. Oh my goodness, nobody yelled at me? You guys should have been lighting up the phones. On this Ripley-Doodle diagram, there should have been an f. Okay, so I've got f double prime. I've got a negative 1 here, a 0 here, and a 1 here. But let's remember that these are vertical asymptotes, right? Now, this is going to be a little tricky, but that's okay. I know that this term right here only spits out positive terms. This thing, because it's cubed, can spit out positive or negative terms. We got to be careful, and then this thing we have to be careful with as well. So let's plug in negative 2. That gives me a negative here, a positive here, and a negative, negative 2,
square 4, 3. No, that's actually going to give me a positive, isn't it? Is that right? Does that give me a positive? That's got to give me a negative. Negative 2. What did I do here? Negative 2. Oh, man. Let me look. Let's see if we can find the culprit. Oh, yeah. I'm sorry. This is going to give me a positive. So then I have a negative. Oh, I was going to be bummed if I had to go back and fix all of that. Negative on top, positive here, because negative 2 squared is 4. 4 minus 1 is 3. So that gives me a negative right there. Okay? How about negative 1/2? Oh, I hate dealing with fractions, but I'm not afraid. Negative 1/2, because that's between negative 1 and 0, produces a negative on top. Negative 1/2 squared is going to be positive 1/4, which will give me positive 1/4 minus 1 is negative. Negative cubed is negative. So I've got a negative on the top and negative on the bottom. So this guy's going to be positive. From 0 to 1, if I put in a positive 1/2, then I get a positive on top. This guy's always positive, and then a negative on the bottom. Positive divided by a negative is always negative. And then if I put in 15 million, then I'm going to get a, let's see, what am I going to get? I'm going to get a positive on top, positive, and then positive here. So that's what it looks like. So let's do a quick summary. Concave up is going to be from negative 1 to 0, union 1 to infinity. I know concave down is going to be, what the heck's concave down? Negative infinity to negative 1, union 0 to 1. That's easy enough. And then, last but not least, let's do inflection points, and then let's get this thing graphed and get out of here. Inflection points at, well, where? Where's the only place that we can have an inflection point? Well, you could say at negative 1 and 1, but the problem is the function doesn't exist there. So those can't be inflection points. Students love to screw up on that. Well, how about at x equals 0? Yeah, that'll work, won't it? I know that 0 exists on the function. It's in the domain. And I know the concavity changes at it. So this is going to be at 0, comma 0. That's the inflection point. All right, so how are we going to graph this thing? Well, we're going to take all of our information. We know the thing always decreases. We know it's got a horizontal asymptote at y equals 0, and it's concave down. It's also got a vertical asymptote at x equals negative 1. So it's got to look, it's got no choice. It's got to look like that. Likewise, I know it always decreases from negative 1 to 0, or excuse me, negative 1 to positive 1, but the concavity changes at 0. So it's got to look something like that, doesn't it? Oh, I'm running out of juice. It's got to look something like that. Now, you might be tempted to level this thing off. If you do, you would be wrong, because if you level this off, that would imply that the first derivative, excuse me, equals 0 at 0, which it clearly doesn't. When I plugged in 0 here, I did not get 0. All right, and that's what it looks like. Excuse me. And then I'm concave up from 1 to infinity, and I decrease. So off I go. Just like that. Now, I realize that you already knew how to do this from your Algebra 2 days. I'm not asking you to abandon that. But what I am asking you to do is, on a problem like this, I'm going to ask you to do the calculus and to verify with the calculus what you already knew graphically from Algebra 2. Also, we can pull out our, whoa, what happened to my idiot? Oh, I closed my idiot box. That's all right. We can be quick with this. TI. Let's have the idiot box pop up. Here it comes. And, no, close, go away. And we'll go y equals, and I'm going to go clear. And then what do we say that was? That was x over x squared minus 1, wasn't it? I think it was. Was it x over x? Wait, what the heck? I'm losing my mind. It's late in the day, guys. It's x over x squared minus 1. All right, so we're going to go x divided by, got to be super careful there. Got to use my parentheses, don't I? Otherwise, the calculator will just see it as x divided by x squared and then subtract 1 from it. So x squared minus 1 and paren. And then, yeah, let's just graph it, see what it looks like. See if we got it right. Boom, boom. Oh, wow, that was crazy. Okay, nailed it. All right, so again, whoa, that's crazy. Again, all that we're doing is we're using our, I'm going to make sure, wow, that was weird. The problem, you guys, the reason those little windows keep popping up is because I'm using a touch, I should turn off the touchpad on this because I'm hitting the hot buttons on my tablet. All right, enough. We know now we can verify using calculus the behaviors of functions. But doing this little bit of dirt work in the beginning and thinking about it, thinking about domain, thinking about intercepts, thinking about symmetry, thinking about asymptotes can really help us. It can save us a lot of time and a lot of energy.
this section in most books is pretty long and onerous. You got a bunch of weird, crazy problems that you have to do, but it's worth doing it. It's worth getting the practice. It's worth doing the algebra on these guys and figuring out and kind of digging down into the mud how the behaviors of these functions affect the derivative. Okay? Well, thank you for your time and your attention. I hope you have a great day, and I'll see you in the next lesson.